Hello chemists, this is Ms. Placino and you are watching Screencast 2.6, which is Quantum Continued. Today we're going to wrap up our study of the quantum mechanical model. Yesterday we talked about how the electrons are going to fill the different energy levels and sublevels according to the off-bar principle, and today we're going to look at how the electrons arrange themselves within a sublevel. So if you think back to what you know about quantum mechanical electron configuration, we know that we've got energy levels. And then within each energy level, there are different sublevels. There's the S, the P, the D, and the F sublevel. You can break that down even further. Within the S sublevel, there is one S orbital. In the P sublevel, you see 3 different P orbitals. In the D, there are 5 different D orbitals. And finally, in the F sublevel, you have 7 different F orbitals. If you're a little lost on what an orbital is, you should probably backtrack to lesson like 2.4 and get some of the basic information about quantum mechanics under wraps first. Let's take a look at the do now. Given what you know about the behavior of like and opposite charges, what are some seemingly fundamental problems with our model of the atom? Explain your answer. Okay, so if we think about it, we've got our positively charged nucleus at the center, and then we have, I'm just going to draw it as a cloud, since we know that, well, we don't know exactly where the electrons are, kind of circling, buzzing around the nucleus, very high energy. When I look at the model of the atom, there are 2 things that really seem to stand out to me that they just don't really make sense, given what you know about like and opposite charges. First off for me is the nucleus. The nucleus, we now know, are where all the protons and neutrons are, and if you think about it, all the protons are positively charged, so it seems like the nucleus should really just break apart. It shouldn't be able to exist because you're packing all those positive charges into an extremely small space. When you take physics, you'll learn about the strong force, and that's actually a fundamental force in nature that physicists discovered to keep the nucleus together. The other thing you might be wondering about when you first look at the atom and you think about it in terms of charges is how do the electrons not crash into the nucleus? Oops. Nucleus. There we go. We know that opposite charges attract. We've got this really positive nucleus, and we've got these negatively charged electrons that are just buzzing around it. And it seems kind of weird that the electrons don't crash into the nucleus or just dive bomb the nucleus or get sucked into the nucleus. So hopefully you're seeing that the atom is really kind of a little bit of a rule breaker as far as what we're used to seeing in our everyday world. Really, when you get down to such small particles as subatomic particles or atoms in general, the rules of the game change. So we don't have to worry about either of these things happening. I guess a little bit like a nuclear reaction, you can get the nucleus to split apart, but in just everyday chemical changes, you're going to see the nucleus stay together and those electrons not crash into the nucleus. All right, let's get into our lesson. This gentleman is Hund, and Hund has come up with a rule about how to fill our orbitals. He says that you have to put a single electron into each orbital in a given sublevel before pairing takes place. And I like to think of Hund's rule as the people on the bus rule, or the people on the subway. I know you guys take the subway every day. Think about it. Let's say you get on at the first or the last stop and you've got an empty train car. You sit basically wherever you want. Let's say they get to the next stop, the door opens, and just one person gets on that train, and they sit right next to you. How does that make you feel? If you're like most people, you're probably kind of weirded out by that. If you don't believe me, give it a try. Make it a social experiment. On a fairly empty subway car, sit directly next to somebody and see how they respond. It's probably going to be unpleasant, so be careful. And if you think about a subway during rush hour, where the train's already really packed and people are standing and you've got an open seat next to you, if somebody comes and sits next to you in that situation, there's a good chance that you don't even think about it. You probably don't even really notice they're there. As New Yorkers, we get really good at blocking other people out. The electrons behave in a very similar way. Whenever possible, they want to spread out as much as they can. And think about it, that makes sense. They're all negatively charged. They're going to repel each other in most situations, so they want space. However, once that sublevel starts filling up and the orbitals have already one electron sitting in each of them, then the electrons are a little bit more willing to share their space. And then they're going to see pairing occur. That's what we mean by pairing, and put 2 electrons in an orbital. We've got this gentleman, and he's Pauli, and he came up with a Pauli exclusion principle. And basically he states that two electrons cannot be in the same quantum state. My guess is you're wondering, like, what on earth is a quantum state? Basically, you can think about it as Pauli saying every electron in the atom is a unique and beautiful snowflake. Even though they are all negatively charged and they're all moving randomly about and we don't know exactly where they're located, no two electrons within a given atom are identical as far as like their energy is concerned. So even if you've got two electrons that are occupying the same energy level and the same sublevel and are in the same orbital, they're not exactly identical. They are what he called spin paired. And let's talk a little bit more about what this spin paired business means. Within an orbital, you've got one electron that's called spin up and the other is called spin down. And this is just a fundamental property of small particles like electrons. And what we mean by spin up and spin down is if you were to take that atom and you were to apply a magnetic field, you can think about the electrons just kind of like rotating. And one of them is going to rotate in the same direction as the magnetic field, and the other electron is going to rotate in the opposite direction of the magnetic field. And really what this serves to do is to minimize the repulsive force that's going to exist between these two electrons. And what's super cool about this is that spin pairing can take place over great distances. So once two electrons or other super small subatomic particles are spin paired, scientists have separated them by miles, sent one spinning in one direction and the other one immediately automatically starts spinning in the opposite direction. It's a really cool property of, again, super small particles. So you might be wondering what consequences this have for you, and it all just has to do with how we're going to fill these orbital boxes. So let's think about how the valence electrons are going to be arranged in an atom like sulfur. S. First thing you need to do is write the electron configuration. So this is hopefully old news for us. If you check your periodic table, sulfur has 16 electrons. Let's back up a second. Oops. So we'd see 1s2, 2s2, 2p6, 3s2, 3p4. Let's just double check and make sure that's 16, 2, 4, 10, 16. All right, I got them. Find the valence electrons, or in this case, just the electrons that were the last ones that you wrote, regardless of what sublevel and energy level they're in. So for us, 3p4 are our valence electrons in sulfur. We're going to draw lines or orbital boxes for each orbital in the sublevel. So if you think about it, it's a p sublevel, and regardless of whether it's the 2p, 3p, 4p, so on and so forth, every p sublevel has 3 different orbitals. You don't have to worry about drawing the orbitals. All you need to do is draw some boxes or some lines. And I'm kind of partial to boxes, so I'm going to draw those. Yeah. You're going to start to fill the boxes, putting a spin-up electron, in other words, just an up arrow in each box, until all of the orbitals are half filled. Put some bad locations for the boxes. And then we're going to fill the orbitals, if we need to, with our spin-down electrons. So let's draw these boxes. Now let's do it this way. So I've got my 1, 2, 3 different orbitals for my p sublevel. And I'm going to put a spin-up electron in each orbital box first. And a lot of times in textbooks or in different resources online, you'll see the electrons just represented by like this half arrow. So I've got 1, 2, 3 of my electrons accounted for. If I look back at my electron configuration, I know that I need a 4th electron. The convention is to go back to the left and pair it up. And that's what it should look like. That's really it. Just a couple things about filling your orbital boxes. You always want to start from the left and fill right. Why do we do that? It's just the convention that scientists have agreed upon. We're going to put spin-up electrons first. And we're going to have to pair electrons spin up and spin down. So let's play a really quick game. I'm going to draw some electron configurations or some orbital boxes, and you got to decide, is this valid or invalid? All right. What do we think? Good or bad? Hopefully you recognize that this is an invalid situation because we've got 2 spin-up electrons in the same box. That's not going to work. So let's get rid of those. How about now? I've got my spin-up and spin-down paired. I must have gotten it right. Wait, the convention is to fill orbital boxes from left to right. Technically, the spin down electron should be moved one box to the left. So that doesn't work either. How about that? Nope, I broke another rule. We start with spin up electrons first, so that is not valid either. How about this one? Yes, this is a valid electron configuration, or I should say orbital box drawing. I've filled from left to right. I started with my spin up arrows. I've got 2 spin down arrows, so we're spin paired, and I've filled the boxes from left to right. So just something to think about when you are working on practice problems. Speaking of, let's check out some practice problems. All right, oops, get through your notes, sorry. So let's do one together, and then we'll give you a chance to do a couple on your own. So if I look at that first one, I've got calcium. And I'm going to go ahead and write the noble gas configuration so that I don't take up quite as much space. So the best way to do that is really to figure out where calcium is on the periodic table. Go back to the last completely filled P sublevel. In this case it would be neon. And then just kind of fill out the configuration from there. It'd be neon 4s2. I'm going to draw my orbital box diagrams, technically for the last sublevel I wrote. I guess I really should put this valence electrons only. So I'm going to go S sublevel. I just have one S orbital. So it's pretty easy to take care of. I've got a spin up and a spin down. Let's do yttrium together as well, element Y, since that was such a straightforward one. I'm going to use noble gas configuration again. If I find yttrium and I backtrack to the nearest noble gas, I get krypton, and I see 4s2, 3d1. Okay, so we're doing it for the last electrons you wrote, not the valence electrons. So in this case, I've got the d sublevel. And I know d sublevels have a total of 5 different orbitals. Now, needless to say, with just this one electron, I'm not going to need all of those boxes. I still have to draw them. This way you've communicated to me that you know how many how many orbitals exist in a d sublevel. Do that. Why don't you try bromine, nitrogen, and nickel on your own? So I've taken care of questions 3, 4, and 5. I've got my electron configurations written out, and I'm going to draw, and actually I've already gone through and drawn my orbital box diagrams for the last electrons I wrote. So I'm going to fill the boxes with you. You can check. I've got 4p5, so I see 1, 2, 3, spin up, 4, 5. Pair them up with spin downs. For nitrogen, I see 2p3, 1, 2, 3. Great, all have filled, that's taken care of. And finally with nickel, I've got 3d8, lots of electrons to draw. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And that's all there is to it. So in my opinion, coming up with those electron configurations is really the hard part. And then it's just remembering some really simple rules. For starters, how many electron boxes or I should say orbital boxes do I need to draw? And that's based on whether it's an S, a P, a D, or an F. And finally, spin up first, go left to right, pair up with spin down. Let's get back to our notes. I want to finish today's lesson by talking about some exceptions that we're going to see to Hund's rule. It turns out that filled and half-filled sublevels are very stable. And what we mean by filled and half-filled sublevels are really exactly what you'd probably expect. A half-filled sublevel has 1 electron in each orbital, and a completely filled sublevel has 2 electrons, spin paired of course, in each orbital. This is associated with stability, and when we say stability in chemistry, we're usually talking about low energy. Atoms want to have low energy. Some atoms can achieve this by reacting. Other atoms can rearrange their electrons to reach these configurations. In reality, there are a number of places in the periodic table where we see this shuffling of electrons for increased stability. I don't want to go through all of those exceptions. I really want to focus in on 2 main parts of the periodic table. So let's talk about that now. Let's take a look at chromium. And chromium, if you were to predict its electron configuration, and based on the space that I've got, I'm going to use the noble gas configuration, you would see argon 4s2, 3d4. So let's think about that for just a second. I'm going to Draw more orbital diagram boxes. That represents my 3D. And here I have my 4s. So my 4s2 shows them spin paired. 1, 2, 3, 4 electrons in a 3D sublevel. If you can look at that picture up at the top, is there any way that you can rearrange or shuffle those electrons to get to filled or half-filled sublevels? Hopefully when you look at this, you see, oh, I could just take one of these electrons from the 4s, and I can promote it to the 3D sublevel, and that's going to give me a half-filled 4s and a half-filled 3D. And that is exactly what we observe occurring when you look at an element like chromium. There are two other places that kind of go through the same shift of electrons, and it turns out that elements in the same vertical column or the same group on the periodic table are going to have very similar electron configurations. So if you look at your periodic table, below chromium, you'll see molybdenum and tungsten. Why don't you pause the video and come up with the expected electron configuration for these two elements, and then based on what we just talked about, the observed electron configuration for molybdenum and tungsten. So we'll bump down to molybdenum, which is exactly one row below chromium. We're going to get a very similar electron configuration expected, Kr5s2 4d4, and just like we saw the promotion of an electron from the s sublevel into the d sublevel with chromium, we're going to see the same exact thing happening with molybdenum. Things are slightly more complicated with tungsten because in addition to the S and the D sublevel, you end up with an F. So we see xenon 6s2, 4f14, 5d4, but exactly the same promotion happens. We take an electron out of the S sublevel and promote it into the D sublevel. So this is the observed configuration. And again, all of these shifts end up giving us a half-filled sublevel for both the S and the P sublevels, and that's just going to increase stability and lower overall energy. If you look at your workbook, you've got another section where this occurs. Copper goes through a similar rearrangement of electrons to get to a more stable or lower energy electron configuration. What I'd like you to try to do is predict the expected and observed electron configuration for copper, as well as see if you can get the other elements that are going to go through similar transitions, come up with their expected and observed electron configurations as well. For copper, we would expect to see argon 4s2 3d9. So just to be consistent, let's draw our orbital box diagram. So we've got the 4s2, the 4s and the 3d. So 4s2 gives us that 3d9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got a filled sublevel with 4s, and we've got kind of almost full sublevel with the 3d. Just like with the last time, we took an electron from the 4s sublevel in chromium and we promoted it up to the 3d sublevel. That's the same thing we're going to see here. So if you were able to predict that we're going to see argon 4s1 3d10, you've got it right. We can move that one electron or one of the electrons from the 4s sublevel into the 3d, giving you a half-filled s sublevel and a completely filled D sublevel, and that's going to be associated with increased stability. Hopefully from the other problem that you did with the chromium, you know that just moving down the periodic table to the rows below copper will give you the other elements that will undergo the same shift. So in this case we have silver. Here's its expected electron configuration. As hopefully you would predict, we're going to take an S electron and promote it to the D to give us again a half-filled and a filled sublevel, S's and D's respectively. And finally, the last element we'll talk about is gold. As with tungsten, a little bit more complicated because you've got your 4f electrons shoved in the middle of that configuration, but it's the same idea. Ooh, typo on the slide. That should say 6s2. So we'll take something from the 6s2, we'll make that 6s1, 4f14, 3d10. So we see that same exact promotion. Again, all of them leading to increased stability, low energy, and essentially happy atoms. So I would suggest, again, get into those practice problems, keep working on electron configuration, and draw those orbital box diagrams. Keep these exceptions kind of tucked away in the back of your mind. You know when it comes to something like your unit test, I'm probably going to put one of these 6 elements on there and see if I can trip you up. So be very aware of copper, silver and gold, as well as chromium, molybdenum, and tungsten. Keep practicing with this stuff. I hope you found this helpful, and I'll see you again soon.